Hello friends, welcome back to Mechanics of Machinery. We'll be today dealing with a topic called Coriolis acceleration or Coriolis component of acceleration. So we have already seen for a rotating link in a slider crank or 4-bar mechanism, there will be two components of acceleration. First one being tangential and second one being radial or vice versa. So if this is radial component, tangential component will be perpendicular to that or normal to that, and the vector sum of that resultant or the vector sum of that will represent the true acceleration. This is the case when link is rotating and a link is fixed and all the reference point in the link remains at the same position. But imagine a link like this and it is having a slider in this position. Let it be link B O A and it is rotating. Now that link is rotated in this position with an angle theta. So what happens? Will the slider directly come to here? No, because that slider is have the capability of sliding. When this link move towards A dash, that slider instead of traveling here, the slider will go up. You can imagine it. When you try to turn a link with a slider, the slider has a tendency to move from its original position. So this movement causes another force and another motion, and that rotation along with the translation or sliding action of this slider causes another component of acceleration to come. That component is known as Coriolis component of acceleration. And when a point is moving on a path and the path is rotating, that means that point can be called as slider and that path can be called as a link. So if a slider is, you can read it like that, if a slider is moving on a link and that link is rotating, then there is an extra component of acceleration other than AR and AT, that is tangential radial, due to the coupling of the motion of the slider and the link rotation. This is known as Coriolis component of acceleration. So if there is a simple link that is rotating, there will be only two components. But where there is a slider also, because of the sliding action of that slider along the link which is rotating, then that component will be known as Coriolis acceleration. And that component is denoted by A with a superscript C. C. Coriolis component, CC. Now, how to determine the direction of Coriolis component? Direction of Coriolis component of acceleration. Sometimes it is known as Coriolis acceleration or Coriolis component of acceleration. So how to determine it? Consider OA as the link. We have four cases. First case, that link is rotating in counterclockwise direction and the slider is moving in upward direction. That may be the velocity of slider and the link is rotating at an angular velocity omega in the counterclockwise direction like this. So this is the angular motion of the link in the counterclockwise direction. So in this case, the angular acceleration and the velocity of the slider will together cause a Coriolis component. That Coriolis component will be acting in this direction. A, C, C. And now consider again the same link acting in counterclockwise direction, but this time the slider is moving downwards. That means omega is in counterclockwise but velocity is moving downwards. Now in that case, the slider will cause an acceleration in the opposite direction. That is, Coriolis component will be in the opposite direction. So both cases the link is rotating in counterclockwise direction, but the slider is moving in opposite directions. Now the link is rotating in clockwise direction. So that means omega is in clockwise direction. Again the slider is moving with a velocity v in the upward direction. Now let's see how that translates into the Coriolis component direction. So In this case, when the link is in clockwise and the velocity is upwards, the Coriolis component will be towards right. And again the link is in clockwise direction, but this time it is moving down velocity, and you can imagine that would be in opposite direction. That is A, C, C. These are the four cases of direction of Coriolis component you should remember. Link is in counterclockwise, slider moving up, it will be in the right towards the left. If this is the case, this will be the direction of Coriolis component. If this is the case, this four conditions are there depending upon the movement of the slider and the Coriolis component of acceleration. And Coriolis component of acceleration only takes place, or there is a Coriolis component of acceleration only when the rotation and the sliding motion happen simultaneously. So now let's see how to derive the formula for a Coriolis component of acceleration. So imagine a slider. Let's say call the slider with the same name B, and link is named as same thing as O and A. And from O we are moving to a this link is rotating, and that A is moved from, let this be the point A, that A is moved from that position to, if you consider a circle here, that will be the case of movement of A when you do undergo rotation, isn't it? So let's cut that circle. Yeah. So that will be the A. Then the new position, let it be A dash. Let it be given in dotted line. So it will be a construction line. So that will be the A. So, and let's assume that slider is B, and we know the slider will not be at exact position of B, it will be somewhere up. So we will see how the slider moves. But let's assume another point called C, and we will see how the slider moves. Just imagine the case. You have a link, you have a slider attached to link, and link is moving in this direction. And let that theta be a small angle d theta. Now imagine the slider. That slider will undergo a motion. This is the slider. That slider will not just translate to here. Will this happen? No. You know, when this link is rotating, the slider has a tendency to move up. So instead of just coming here, the slider will move like this. Along with the link rotation of the link, the slider will undergo a motion similar to this. This motion is due to the Coriolis component of acceleration. Actually, the slider will move to an intermediate position and then come to a rotating position somewhere like this. This will be the final part of the slider, but it will undergo that motion by slowly coming from here, then rotating, like turning here, then it will come to somewhere in the final position, somewhere there. We don't know exactly, but somewhere there. Let that be the position of the slider, final position of the slider. So we have seen how the slider translates. So let that be the final position of the slider. So what we have seen is that we can imagine also that slider will not just translate to the final position, it will undergo a motion. So let's assume if there was simple translation, the slider will actually undergo a circular motion like this. If this was the circle, slider would have undergone only that much. So let's assume that was the motion of the slider. Okay, so we don't need that part. Yeah. So if that was the translation, that would happen. But in the case we know, actually the slider moves in another way. So let's take a point in the current position of the slider. Yeah, that point will be that. Okay, so let's assume this point is C. This is the final position F, and let this be D, and we can draw a perpendicular from D to the arc EC. Let that be point E. Let's put it in dotted lines. So now we have to do some, and this is moving with an angular velocity omega. So this motion is happening with an angular velocity omega. So we can write omega in this direction, omega. So now slider has three stages of motion we can get from this. Slider first moves from B to D, then D to E, then E to F. You can imagine like slider moving in this direction. But that is an imaginary position. Still there is a position. Because the slider does not come to D, if there was no component of acceleration, then slider would have to come to D. Because of that sliding action and the rotation of the link, the slider actually, instead of coming to D, it is going to F. That is, something is pulling that slider along that link to slide off to the position F. That pulling is known as component of acceleration. Scientists was trivialized because the slider is not coming to D, it is going to F. Why that? That component is known as Coriolis component of acceleration. I hope what is Coriolis component is now clear. Now let's find how to get the Coriolis component of acceleration. So we know all these are arc length. You might have learned arc length is equal to radius times angle theta. This is a formula you might have learned in geometry. So let's take each of the arc length. Arc EF. Arc EF can be written as larger arc CF minus CE. So CF minus CE. And you can see from the geometric position that if this is perpendicular to the arc, then BD would be equal to EF. B is in this position. Let's mark that B correctly. Let's assume the B is on the point on here. This is the point B. So BD will be equal to EF because this is a perpendicular line to the point of arc. And the theta remains the same for both. So geometrically there is a relation. So we can take, instead of EF, so EF would be equal to CF minus BD. CE would be equal to BD. This arc will be equal to this arc. These two arcs will be equal because that ED is perpendicular. So we can write that along here, since BD arc is equal to CE arc. Now we know arc length is equal to radius times the angle. So CF is having a radius of OF, or CF is having a radius of OF, and OF will be equal to OC because we see O to C is same as O to F. So OC times d theta angle, radius into theta, minus BD is having a arc with radius B, OB times d theta. That will be the equation. OC times d theta and BD times theta. And we can write that OC minus OB times d theta, and you can see OC is the larger thing and OB is the smaller thing. So this length minus this length will give you OC minus OB will give you this BC. So let's rewrite that. So EF is equal to BC into d theta, since OC minus OB is equal to BC from that link. So now if d theta is very small, that means angular displacement is very small, is approximately equal to 0 or very small, then BC will be equal to DE. BC means this one and DE means this one, because if that angular position very small, then these two things will come like a parallel lines separated by a small distance. Since now it is also parallel, but it will have equal length if this angle remains very small. You can see it from here. If this line was coming close to that, that D will come very close to being a 90-degree line. So that BC will be same as DE. So as the angle reduces, that BC will be equal to DE. So taking for small angle, BC will be equal to DE. So for a very small angle, BC equal to DE, and you can write now EF arc will be equal to DE theta. DE theta. That will be equation number 1. Okay, I made a mistake. This is BC, okay? This is BC, not BD. This is BC. Here it is written BC d theta. So BC will be equal to DE theta. Now we know DE is nothing but, you see, what is DE? DE is nothing but the displacement of the slider. Displacement of slider in vertical direction. So this, we know velocity is equal to displacement by time. So I am not going to write it. So we can write, instead of that, displacement is dE. So we can write it as, if v is the velocity of the vector, we can write dE is equal to v into the time, that is dt, where v is equal to velocity of slider. If d is the displacement of the slider, then v is the velocity of slider. So d is equal to v dt. And similarly, we know omega is equal to angular velocity, that will be angular displacement by time, and we can write angular displacement d theta is equal to omega into dt. So applying these relations in equation number 1, we can write EF, that is arc EF is equal to, it was dE times dt d theta. So dE will be v dt times omega dt. V dt times omega dt. That will be is equal to omega into v into dt square. Now considering the Newton's equation of motion, and we know S is equal to ut plus half at square if acceleration is constant and u is equal to, that is initial velocity is equal to 0, we can write it as S is equal to half at square. And now applying the same thing here, here the displacement is actually EF, isn't it? Displacement is actually EF, and the corresponding acceleration is Coriolis component of acceleration. We consider this displacement EF, and we know the EF is caused by the acceleration known as Coriolis component of acceleration. So we can substitute it as S is equal to EF, and corresponding A will be equal to acceleration with the Coriolis component or Coriolis component of acceleration. So substituting that like this, EF is equal to half of Coriolis component of acceleration times t square. Here the time is dt, so dt square. So now substituting back, EF we have already found it as omega into v into dt square is equal to dt square is equal to half of acceleration and dt square. So from here you can see that dt square cancels and you will get Coriolis component of acceleration is equal to 2 times v omega. This is the equation for Coriolis component of acceleration. This is important. Derivation may be asked. 2 times v into omega, where v is the sliding velocity and omega is the angular velocity. So this is the acceleration due to Coriolis component or Coriolis component of acceleration. Hope you understood it. We will continue with this tomorrow or day next session. Thank you.